Now that we understand the basic design and specification of the elements of our subsurface pump, we should turn to the next component in our pumping system, the rods. In doing so, we must cover two major topics. First, the composition, strength, and variety of rods that are available. And second, the manner in which a rod string is designed so that it is able to withstand the loads placed on it. In each case, we shall refer to the API standards or specifications to guide us. In API Specification 11B, we find the fabrication specifications for sucker rods, including pony rods, polished rods, couplings, and subcouplings.
In reviewing this document, you will see that sucker rods are usually made in 25-foot lengths, except in California, where they come in 30-foot lengths. The 6 standard rod sizes are 1/2, 5/8, 3/4, 7/8, 1 and 1 1/8 inches in diameter. Rods are normally made of steel with a composition of iron exceeding 90%. Other elements are added to the steel alloys to add hardness, reduce oxidation, and combat corrosion. The choice of sucker rods is essentially a choice between API Grade C rods, which have a minimum and maximum tensile strength of 90 and 115,000 psi, and Grade D rods, which have limits of 115 and 140,000 psi. Tensile strength refers to the maximum load that can be sustained by the rod. It has become standard practice to run Grade D rods, except where corrosion is severe or where there is concern with regard to H2S embrittlement. A higher tensile strength rod has been introduced which may be used in special applications. All these types of rods must be handled with care. If damaged, they may lose their high strength properties. Fiberglass rods were introduced in the early 70s and are only now gaining acceptance. They are appealing because they weigh about 70% less than steel rods and are less prone to corrosion. In addition to the environment to which rods will be exposed, we must be careful not to exceed the maximum allowable rod stress. In order to calculate the maximum rod stress, we use the modified Goodman equation, or as seen in many publications, the modified Goodman diagram. The equation states that the allowable rod stress, S sub A, is equal to 0.25 times the minimum tensile strength of the rod, T, plus 0.5625 times the minimum rod stress, all multiplied by the service factor, SF. If we know the API grade, then we have a published value for T. The minimum rod stress is either estimated for our proposed application or measured directly. We shall see later that it is equal to the minimum polished rod load divided by the cross-sectional area of the rod. The service factor depends upon the environment in which the rods will be placed. As we see here, it will have a value of 1.0 for API grades C and D rods used in non-corrosive environments, but values of less than 1 for saltwater and H2S environments. Note that the service factor for corrosive environments is lower for grade C than it is for grade D rods. We may use the modified Goodman equation to calculate the maximum rod stress for a grade C rod in a saltwater environment where the minimum stress, S min, has been calculated to be 10,000 psi. T, the minimum tensile strength, is 90,000 psi, and the service factor for saltwater for grade C rods is 0.65. Using the modified Goodman equation, we find the maximum allowable rod stress to be 18,281 psi.
In general, maximum allowable rod stresses under working conditions should not be higher than 30 to 40,000 psi. The newer high tensile strength rods are rated at 40 to 50,000 psi in non-corrosive environments.
So far, we have discussed the design of a rod string of a single diameter. However, the most accepted way of designing a rod string longer than 3,500 feet is to use a tapered string, That is, to have several different lengths of rods of different diameters, with the largest diameter rod at the top and the smallest at the bottom. This tapered string may consist of as few as 2 and as many as 4 different size rods. The fundamental design criterion used for a tapered rod string is that the string have the same unit stress at the top rod of each section. That is, the rod loads in the top rod of each section, divided by their respective cross-sectional areas, are equal. This provides for a safe design, even in the event that some corrosion pitting takes place.
In order to select the appropriate tapered rod string for a specific well, we turn to the API design tables. These tables are published in the API Recommended Practice 11L, referred to as RP11L. A copy of this publication is contained in your manual. It contains the fundamental design calculations for sucker rod pumping systems and is one that we shall refer to quite frequently.
If we turn to page 7 of that manual, we see tables that provide us with the appropriate tapered rod string design. In the first column, we see the API rod number designation. In the second, the pump plunger diameter in inches. In the third, fourth, and fifth, we see certain rod constants. And in columns 6 to 11, we see the percentage of each diameter of rod that should be used for a specific API rod number designation. For example, if we have a plunger diameter of 1.06 inches and select API rod number 54, then looking to the right-hand side, we see that 44.6% of our string should consist of 5/8-inch rods and 55.4% of half-inch rods. Alternatively, we might select API rod number 75 for the same diameter plunger, and here find that 27% of our rod string should have 7/8-inch rods, 27.4% with 3/4-inch rods, and 45.6% with 5/8-inch rods.
This would provide us with a different rod makeup and different rod characteristics than the first design. But both would meet our design criterion. As we shall see shortly, the key to the API design procedure for pumping wells is one of trial and error. This includes the design of rods. We initially select a tapered rod string design, carry through our calculations, and see whether the rod stress placed on the rods exceeds the maximum limits for the class of rods used. If it does, well, then we must select other rod number designations until we find one which will satisfy design limitations.
For the 1.06-inch diameter plunger, we found 2 designs that might be used. Converting the percent values to actual rod lengths, the first design for a 5,000-foot well would consist of 2,230 feet of 5/8-inch rods above 2,770 feet of half-inch rods. Since rods generally come in 25-foot lengths, we would have to adjust these 2 numbers to 2,225 and 2,775 feet respectively. For the second design, we would end up with 1,350 feet of 7/8-inch rods at the top, followed by 1,375 feet of 3/4-inch rods, and below that, 2,275 feet of 5/8-inch rods. In our API design calculations, then, we would select one of these and see whether it meets our design limitations. If it did not, we would have to move to a heavier rod string. Alternatively, if the rod string was over-designed, we might select a lighter string.
Now that we know the basic properties of rods, we should turn to the calculation of rod loads during pumping operations. We must know these rod loads in order to design our surface facilities. Later we shall see that rod loads are measured at the surface during production operations in order to learn what is occurring downhole at the pump.
As we consider the motion of this polished rod and the action of the valves in the subsurface, we realize that the load it must carry varies during the pumping cycle. Its maximum load occurs shortly after the beginning of the upstroke. When the traveling valve closes, the polished rod must carry the full weight of the fluids, the rods, and the added inertial effects that occur when the motion of the rods are reversed. The minimum load on the polished rod will occur shortly after the polished rod begins its downward motion and the traveling valve opens. At that point, the rods no longer carry the fluid load and the inertial effects are reversed, thereby reducing the total rod load to a value which is below the weight of the rods in the produced fluids. Let's see what difficulties arise when we attempt to calculate the maximum and minimum polished rod loads. We begin with the peak polished rod load, or PPRL, which we know must be equal to the weight of the rods in air minus the buoyancy of the rods in the produced fluids plus the weight of the fluid column supported by the plunger area plus the effects of the inertial and acceleration forces on the rods. Calculating the weight of the rods in air is quite straightforward. We look up the API tables for the rod design that we just referred to, find the average weight per foot of rods in our tapered rod string, W sub R, and multiply that by the total length of the rods in feet, L. The average weight of the rods is 1.566 pounds per foot, and the length of the string is 5,000 feet, and so the weight of the rods in air, W, is 7,830 pounds. The second term, the buoyancy of rods in the produced fluids, is equal to the weight of the fluids that the rods displace. We may calculate this term by saying that it is equal to the density of water, 62.4 pounds per cubic foot, multiplied by G, the specific gravity of our produced fluids relative to water, multiplied by the weight of the rods in air, W, divided by the density of the steel. The density of steel is equal to about 488 pounds per cubic foot. The buoyancy, then, is equal to 0.128 multiplied by G multiplied by W. If we assume the density of our produced fluids to be 55 pounds per cubic foot, giving us a value of 0.88 for G, then, as we see here, the buoyancy effect is equal to 0.128 multiplied by 0.88 multiplied by 7,830, the weight of the rods in air, or 882 pounds. We obtain a value for W sub RF, the weight of the rods in fluid, by subtracting the buoyancy of the rods from their weight in air. It is equal to 6,948 pounds. F sub 0, the weight of the fluid column supported by the net plunger area, is equal to the density of the produced fluids multiplied by the net plunger area multiplied by the height of the static fluid level. The net plunger area is equal to the area of the plunger minus the area of the rods. The suggested API procedure, however, disregards the area of the rod in this calculation. We shall do likewise. Filling in, then, we have the density of the fluid as equal to 62.4 multiplied by G. The area of the plunger in square feet is equal to pi multiplied by the square of the plunger diameter in inches divided by 4, multiplied by 144 to convert square inches to square feet. The fluid level is given the designation H in feet. The units are consistent, and F sub 0 will be in pounds. Collecting terms gives the general equation for F sub 0 in these units. For our sample case, G is equal to 0.88. The plunger diameter is 1.06 inches, and we will assume the static fluid column height to be equal to the pump depth of 5,000 feet. This gives a fluid column weight of 1,681 pounds. We now know that by summing the first three terms, we obtain a polished rod load of 8,629 pounds, plus the effects of the inertial and acceleration forces. The behavior of the polished rod is very complex, and predicting the effects of these forces can be difficult. Not only does the rod string stretch and contract in response to a cyclic motion which is not simple harmonic, but also to a crank and pitman motion which is different for each different type of pumping unit. Because of the elasticity of the sucker rod system, stress waves run up and down the rod in response to the various forces that can affect the rod. There are several alternatives for including the effect of inertial and acceleration forces on our polished rod loads. The alternatives are, first, to make simplifying assumptions about the behavior of the rod and the pump motion. This has often been done in the past, but need no longer be done today. A second option is to use empirical correlations that have been prepared on the basis of many repeated observations of pump behavior. This is the API design procedure. It is based on work done at the Midwest Research Institute, where rod pumping systems were simulated on an electronic analog computer. By simulating a wide range of pumping conditions, the Institute was able to develop correlations which can be used to predict polished rod loads. A third option that may be used to calculate rod loads is to solve the nonlinear partial differential equations, which represent the behavior of the rod string.
Gibbs, originally on his own and later with Neely at Shell, solved these types of equations in an effort to analyze pump operation rather than pump design. Their work is based on the use of a known value of peak polished rod load at the surface in order to calculate the behavior of the pump in the subsurface. In order to calculate the peak polished rod load without making simplifying assumptions then, we are left with the second option, the one followed in the API design procedure. Because this procedure is fundamental to the design of our surface pumping system, we should take a few minutes to learn the empirical correlations and the way in which they are used to calculate polished rod loads and other values needed in our pump design. Experimental work conducted at the Midwest Research Institute on sucker rod pumping, later adopted by the API, consisted of numerous experiments run on an analog computer, representing a wide range of pump operating conditions. The results are correlated on the basis of two dimensionless variables.
The first variable is the dimensionless pumping speed, and the second, the dimensionless rod stretch. The dimensionless pumping speed is equal to n divided by n sub 0, or n divided by n sub 0 prime. The first dimensionless variable is equal to the pump speed in strokes per minute divided by the natural frequency of the string. The alternative dimensionless variable for pumping speed is equal to n over n sub 0 divided by f sub c, the frequency factor of the rod string. Note that f sub c is equal to 1.0 for an untapered string and is greater than 1 for a tapered string. In the event that an untapered rod string is used, the two dimensionless variables are equal. We shall see very shortly that for several correlations, one of these variables is used, and for others, the other is used. N sub 0 is equal to A divided by 4L. A is equal to the speed of sound in steel rods, and is customarily given a value of 16,300 feet per second. The dimensionless ratio, then, is equal to NL divided by 245,000. N over N sub 0 prime is obtained by dividing this term by F sub C, the frequency factor of our rod string. Values for the frequency factor are found in the API tapered string design tables, as we shall see shortly. We note that for a given or assumed pumping speed, rod length, and frequency factor, we may calculate a value for this dimensionless variable. Before doing so, we should understand the second dimensionless variable of importance, the dimensionless rod stretch. It is equal to F sub 0 over SK sub R. F sub 0, as we saw earlier, is the static fluid load in pounds. Note that S is the polished rod stroke length in inches, and that K sub r is the spring constant of the rod string. Its value is also given in the API rod design tables. It represents the load in pounds required to stretch the rod string the length of the polished rod. We see then that the dimensionless rod stretch term represents the rod stretch caused by the static fluid load, given as a fraction of the polished rod stroke length. For example, if the term has a value equal to 1, then the rod string will stretch an amount equal to the length of the polished rod stroke. We note here again that for a known or assumed polished rod stroke, the value of this dimensionless variable may be easily calculated. We should add one word of practicality at this point. It has been observed by a number of specialists that under-travel and over-travel of the pump can be prevented if n over n sub 0 prime does not exceed 0.35 and f sub 0 over sk sub r does not exceed 0.50.
With these known values for the two dimensionless variables and the results of the work done at the Midwest Research Institute, 5 correlations were published and are available in API RP11L. These 5 correlations allow us to develop systematically the API design for a pumping unit. The first 3 correlations affect the rod and pumping system, specifically the plunger stroke, the peak polished rod load, and the minimum polished rod load. The last 2 are used to calculate peak torque and polished rod horsepower. Let's look at these correlations by referring to an example. We shall do so using the data from the sample problem we have been discussing.
The given data includes a fluid level, H, and pump depth, L, of 5,000 feet, a tubing size of 1.9 inches. The tubing is anchored. We assume an API sucker rod number 75, consisting of 1,350 feet of 7/8 inch rods, 1,375 feet of 3/4 inch rods, and 2,275 feet of 5/8 inch rods will be adequate for our needs. These grade D rods have a maximum rod stress of 34,000 psi. The plunger diameter D is 1.06 inches, and we shall assume for preliminary design purposes that the pump speed N is 16 strokes per minute, and that the polished rod stroke length S is 64 inches. G, the specific gravity of the pumped liquid, is 0.88. A quick calculation tells us that these data will provide a pump displacement of about 135 barrels per day. Using inflow performance calculations discussed in Module 102, we expect the production to be about 100 barrels per day. Our design then must satisfy this objective and allow a little downtime for maintenance. We see here the first correlation, the one which allows us to calculate the plunger stroke length. On the left, we see the term S sub P over S, the bottom hole pump stroke length divided by the polished rod stroke length. This ratio reflects the effect of rod stretch on the effective rod stroke length. On the horizontal axis, we see the dimensionless pumping speed, N over N sub 0 prime, the first dimensionless variable, and on the graph itself, we see different curves for different values of the second dimensionless variable, that for rod stretch. Since we know or can calculate the values of these two dimensionless variables, this correlation may be used to calculate a value for S sub P over S. In our example, N over N sub 0 is equal to N multiplied by L divided by 245,000. For our data, this equals 0.326. N over N sub 0 prime is equal to this value divided by F sub C. For our selected rod string, F sub C is equal to 1.191. And so N over N sub 0 prime is equal to 0.274. The dimensionless rod stretch is equal to F sub 0 divided by Sk sub r. As we saw earlier, F sub 0, the weight of the fluid supported by the rods, is 1,681 pounds. S, the stroke length in inches, is 64, and the reciprocal of K sub r is equal to the elastic constant for our rod string. We can find its value in the API tables. It is equal to 0.997 times 10 to the minus 6 multiplied by the pump depth of 5,000 feet. With this data, we calculate the dimensionless rod stretch to be 0.13. We note here that the values for both n over n sub 0 prime and f sub 0 over sk sub r do not exceed the limits of 0.35 and 0.50 mentioned earlier. With known values for the two dimensionless variables, we turn to our correlation. We start on the horizontal axis with a value for n over n sub 0 prime of 0.274. Then move vertically to a point represented by a dimensionless rod stretch value of 0.13 between the 0.1 and 0.2 lines, and then over to the vertical axis to find a value of 0.98 for S sub P over S. If the tubing is anchored, as it is, this means that the bottom hole plunger stroke length, S sub P, is equal to 98% of the polished rod stroke at the surface. This means that for a surface stroke length of 64 inches, our bottom hole stroke length will be 62.7 inches. If the tubing were not anchored, then we would subtract from this plunger stroke length an additional term, which accounts for the tubing contraction during the upstroke. This term is equal to the coefficient of elasticity for the tubing, E sub T, measured in inches of stretch or contraction per pound force imposed per foot of tubing, multiplied by the pounds of force imposed, F sub 0, multiplied by the tubing length, L. Values for E sub T for standard size tubing are given in RP11L. For the 1.9-inch tubing, it has a value of 0.5 multiplied by 10 to the minus 6. With F sub 0 equal to 1,681 pounds and L equal to 5,000 feet, the plunger stroke length is reduced an additional 4.2 inches if the tubing were unanchored. In this case, the net plunger stroke would be 58.5 inches. We are now able to calculate subsurface displacement. We use the pump displacement expression developed earlier and are given values of pump stroke length in inches, pump speed in strokes per minute, and plunger diameter in inches to give us the pump displacement in barrels per day. In this case, it is about 131. This more than meets our expected inflow rate of 100 barrels per day. In fact, it allows us about 20% downtime per day for maintenance. However, had it not met our production objective, we would now revise our assumed pump data and repeat the calculations. To calculate the production rate at the surface, we must incorporate the pump efficiency considerations mentioned earlier. Let us now turn to the second correlation, which allows us to calculate the peak polished rod load. Once again, we see our dimensionless variables, whose values we know, plotted in the same general locations. The horizontal axis is simply n over n sub 0. It is the vertical axis which is now changed. In this case, it is equal to F sub 1 over Sk sub r. We are already familiar with the terms in the denominator, having calculated their values earlier. F sub 1, the only unknown, is referred to as the peak polished rod load factor and may be obtained quite easily. Let's see how it is done. Our dimensionless pumping speed, N over N sub 0, as we saw earlier, is equal to 0.326. The dimensionless rod stretch we also have already calculated. It is 0.13. Thus, the value for F sub 1 over Sk sub r is equal to 0.37. Because we know the value of Sk sub r, it is possible to calculate F sub 1. Note that F sub 1 is the term which we add to the weight of the rods in the produced fluids to give us a value for the peak polished rod load in pounds. It represents, then, two terms, the weight of the fluids and the load caused by the inertial acceleration forces. The peak polished rod load, then, is equal to the weight of the rods in fluids, W sub RF, plus F sub 1. Or in terms of our correlation, it is equal to W sub RF plus the term F sub 1 over Sk sub r multiplied by Sk sub r. For our sample problem, we remember that the weight of our API number 75 rod string in the produced fluids was calculated to be 6,948 pounds. The dimensionless term, as we just saw, is 0.37. All we need is a value for Sk sub r. K sub r, the spring constant for our rod string, is equal to the reciprocal of the coefficient of elasticity of our rod string, E sub r, multiplied by the length of rods, L. E sub r for our rod string is 0.997 times 10 to the minus 6, and L is 5,000 feet. This gives us a value for K sub r of 200.6. With a polished rod stroke length, S, of 64 inches, we calculate Sk sub r to be 12,838 pounds. Now we are able to calculate the polished rod load for our example. It is 11,698 pounds.
This value represents our best estimate of what the load will be and should be used for design purposes. Under actual operating conditions, it will be different, but should not be significantly different. Now that we know how to calculate the peak polished rod load, let us turn to the third correlation, which gives us a method for calculating the minimum polished rod load. We remember that the minimum polished rod load occurs just at the beginning of the downstroke, when there is maximum downward inertial force and the fluid load is no longer carried by the rods.
In our correlation, we see once again our two dimensionless variables in their same location. But now on the vertical axis, we see the term F sub 2 divided by Sk sub r. F sub 2 is referred to as the minimum polished rod load factor. Once again, with a value on the horizontal axis of 0.326 and a dimensionless rod stretch value of 0.13, we find that the point of intersection on the vertical axis is at 0.21. Knowing the value for Sk sub r, we can calculate a value for F sub 2. This term represents the amount that must be subtracted from the weight of the rods in the produced fluids to give the minimum polished rod load. As such, it represents the inertial and acceleration force at the point of minimum load. Its calculation proceeds directly parallel to that for the peak polished rod load. We expand the term for F sub 2, then fill in all the known values on the right-hand side. In doing so, we find a minimum polished rod load of 4,252 pounds. Once again, we should point out that this value is used for design purposes and that its actual value after installation may be different.
We began this unit by discussing the types and grades of sucker rods and continued on to the design of sucker rod systems. We then attempted to calculate directly the peak polished rod load because we knew it was needed in order to design our surface system. We found that direct calculation was difficult, and so we turned to the three API correlations, which allowed us to calculate effective plunger length, and thus pump displacement, peak polished rod load, and minimum polished rod load. There's a little more yet to do, but before going on to the design of the surface system, let's stop at this point and work exercises 6.6, 6.7, and 6.8.